Okay. So in the previous two sessions, we on fraud detection and prevention, we learned the types of errors in hypothesis testing, some basic data structures such as list, array, stacks, queues, and trees. I introduced you to Google Collaboratory, where you can run Python and Jupyter notebooks. We saw what a data frame looks like in Pandas, what a basic flow chart is. And then I introduced the idea of a cost function, which really is it makes its way into almost all of machine learning and analytics in the future. It was a very elementary idea of a cost function. So what we looked at the cost function by looking at a process like this for trying to prevent fraud, right? And this process is extremely elementary. It is just a two-step process, but it was sufficient for us to write down what a cost function looks like and see what needs to be optimized. However, the process we outlined with this simple process is it's called a rules-based approach for fraud prevention. It is there in almost every system, but it has its limitations. For example, it cannot predict new types of fraud. It really cannot respond to new situations. It is something that the team will constantly keep modifying, but it is not how you recognize new types of fraud, etc. And for that, I had mentioned that you actually need an involved process that involves more complex statistical techniques or machine learning. And today's lecture, I will introduce you to at least the concepts of some of those processes. So I was planning to I am planning to introduce you to what is called supervised learning, how it is different from what is otherwise known as unsupervised learning in types of the in the kind of data it deals with. Then we will go through some of the common techniques used for supervised learning, but we will really focus on what is called decision trees because they're very elementary to understand. And then in unsupervised learning, which is, unlike supervised learning, where I'll show you soon, unsupervised learning does not require your data to come pre-labeled. You can really spot patterns in it. And the techniques related to that, but we will focus on one method called k-means. And then in Monday's lecture, to the data sets that I already introduced you to in the previous session, we will apply these two methods. And so it will be a live coding session and it will be very straightforward. Supervised learning always involves taking an algorithm that's usually already been coded up and you train it on some data. And this data that you're training it on needs to be labeled. Once the training is over, it can now process unlabeled data and it can classify it. So for example, the training data, you will tell your algorithm that this is a star, this is a rectangle, this is a triangle, this is a square, this is a circle, etc. And once that step is over, you can give it a large number of shapes like this, and it will classify them into stars, circles, and triangles. That is the basic idea of supervised learning. The basic nature of it is that the data needs to be labeled. So in the example we looked at last week, if you remember, there was an entire column called is fraud, and that is possible because the data of these transactions, each row of the data set we looked at corresponds to a transaction that has happened in the past. The bank that has released this data set after anonymizing it has already carried out quite a bit of investigation, and they have decided that some of these were fraudulent transactions and some of them were not. And because of this label, you are now able to instruct a machine learning algorithm that, hey, the ones where it was 0 was not a fraudulent transaction, but the ones where it was 1 were a fraudulent transaction. But the thing to remember about data like this that you feed to any algorithm for classification is that the labels are probably wrong. Now, some of them, at least, a fraction, in the sense, the ones that are that have been identified as fraud in a data set like this are probably fraudulent. Some of them maybe could have been falsely identified also. I introduced type 1 and type 2 errors. But there are probably hidden fraudulent transactions among the ones that the bank considers was okay, and they'll realize it only later, and they'll because maybe nobody noticed it and reported it, and it was a normal transaction. It passed off as a normal transaction. So you usually cannot use only supervised learning for these purposes. You have to use both hand in hand. So there are supervised learning usually when it is applied on discrete data. It is usually a classification problem. For example, this earlier fraud versus not fraud, and it's just a matter of classifying which group your data set falls into. But on the other hand, if it is on a continuous distribution, this is not an example that that applies to the previous data set, but it is instead of classification, it's called regression. And then it can, the example would be, for example, predicting demand based on the COVID positivity rate in the last per month basis. Then you can train what will be the demand for medical oxygen in a region, in a district, in a state, based on the previous data. And since those numbers are not fraud or not fraud, or like a Boolean yes or no answer, they are continuous. The problem is considered a regression problem. So one of the first problems you'll run into when you're trying to train an algorithm is that you will have unbalanced data. And we already saw this in the data set we looked at in the last exercise. There were 6,362,620 entries in total, out of which only 8,213 entries were marked as fraud. So that's roughly of the order of like 0.1%, right? Or roughly 0.1% of the data were fraudulent. And this is not really desirable, because most of the pre-written algorithms in machine learning will require balanced data sets. They prefer to be trained on balanced data sets. So some of the techniques that are used to balance a data set, which is so seriously unbalanced, is to either you can randomly oversample this. That is, you take each of these 8,213 entries and create duplicate entries from it. Let's say 5 duplicate entries per entry, and then you have 40,000 entries. And so then you get a less unbalanced data set, or you can scale it up by any number. You can also undersample your data. You can eliminate many of the data sets randomly from this, many of the data points randomly from this data set, so that it comes down to this level. But as you can see, these processes are not the preferred way. It is the crudest way to deal with unbalanced data. The most popular way, and one of the first things you'll be taught in almost any data science course, is something called synthetic minority oversampling, which is to take these 8,213 data sets and create fake entries using existing entries. So how they do that is, you take two known, for example, in this data set, what we will work out on Monday will be, you will take two known fraudulent data sets, F1 and F2, fraudulent transactions, within the data set. And then you'll create a third one by using this expression, where X is a random number uniformly distributed between 0 and 1. So what you have is, this is your minority data set, this is your majority data set. Think of the positions of these data sets as the feature variables. So a data like this, which has these rows and these columns, each of them are different transactions. Each of the columns correspond to what is called a feature. This is a term commonly used in data science. What is called feature is the different columns of data. You will later on come across terms like feature vector, etc., and that just means the collection of features you have selected. So a type, the amount, the origin, the old balance in the account before the transaction happened, the new balance after the transaction. These are all features of the data. And so in this case, you are looking at a two-dimensional data set. and each feature is an x-axis and a y-axis position, right? Or you can think of it that way, but this is just a representation to tell you. And the oversampling technique, what it does is it just creates a new data set that is a weighted mean, the weighted average of two existing. Sorry, it creates a new entry in your data set that is the weighted average of two existing entries. So this is one way to upsample when you have very sparse statistics. So you can see that many fake entries have been added, and each of these fake entries are usually the means of other points within the data set. This is by far the most common technique, but this can go horribly wrong. For example, in this picture, you see that the line that divides the two, the majority and minority data sets, it's almost a line. But if it was a concave feature like this, and you picked one fraud transaction from here and another fraud transaction from here, and you do a synthetic oversampling, you would end up with a fake data set which is inside your majority data set. So one has to be very careful when applying techniques like these, even though these are the most common ones, that the spaces you're looking at are convex, that they are the descriptions are linear, etc. But they are, these are things to keep in mind when you really work with real data. You should visualize them and make sure your oversampling is not going wrong. So one of the first classification algorithms, and the easiest to understand, is something called a decision tree classifier. You can think of it this way. Your data has, like in the previous case, in this case, I'm looking at an example of data that have two features. So X1 and X2. So unlike our transactions of within accounts, which had, I think, 17 features, here you have just two features. And a decision tree is a collection of nodes joined together by these decisions, sort of like the flow chart that we showed. Each of this is called a layer. So this decision tree has 6 layers, 1, 2, 3, 4, 5, 6. And the number of layers is a feature of the decision tree that you will have to choose when you decide to use it. The other feature is that a decision tree is very simple. You go based on a condition. For example, if one of your features, X1, is less than a certain value, you take that corresponding branch. If it is greater than or equal to that certain value, you take another branch. And you follow these decisions. You follow these decisions through to the end, and you can classify each of your object. And as you can see, the spatial distribution of the colored points in this picture is nicely captured by this decision tree. The process of training a decision tree is the process by which you decide on various aspects of this tree. This tree is already well defined, but the training is the process by which you define this tree, which is which features to split the data by and what order. So here we have chosen that X1 is the feature you will go with first, and that X2 is the feature you will go with second, and then you have additional layers with X2 alone. And so that is a decision to be made while training your data, while training your decision tree. And then here you will also notice that the values are already specified, whether it's 1.2, 1.9, 2.4, where exactly to cut. And those values are also chosen during the training process. So you have a process by which you have an algorithm called a decision tree, and you train it with data. And in that process, it will learn what order to apply to cut on the features in, and what are the values to cut at. Now, the concepts for implementing a training algorithm, like if you want to code it up, are I guess I would say sort of beyond the scope of this lecture, at least the introductory lecture, but we can nevertheless use it. And the vast majority of data scientists, people who use this in the industry, do not actually know what is going on inside each algorithm. The information is there for you to to look up, but they don't use it. They use pre-written code in a black box sort of way. Even though decision tree classifiers are considered white box algorithms in the sense that it is very transparent what is going on inside. Each decision tree that has been trained can be visualized in this way, and so it is very easy to understand what is going on. The algorithm for training a decision tree will evaluate a bunch of things at each nodes, such as these concepts, which you can look up later, but in more advanced modules, we will try and teach this to you. And it is a collection of decisions. Thankfully, for the sake of this lecture, I will not be introducing these concepts, but you can look it up. One of the most important things of any such trained model is that a good model must not only fit the training data, but also accurately classify records it has never seen. That is, you train it using some 4,000 fraudulent events, and if you give it those same 4,000 events, obviously it will later tell you this was fraud or not, because it already has the data label with which it has decided that with which it was trained. But if you show it some new data which you have the labels for, but you don't give it the label, and it is able to correctly predict it, that is the meaning of that is how you decide if your training was successful. So usually what happens is that in a data set like this, where you have some 8,213 fraudulent data sets, and you don't use all of them for training, you will split it further. You will decide to use 6,000 for training and 2,200 for testing, and then you will see how the performance of the tree is on both the training and testing data sets. And if the training and testing data sets perform very differently, then you have something called overfitting or overtraining. It is not at all a desirable property. And at that point, you have to make some decisions, like make your tree simpler, reduce the number of layers, etc. These are usually things people learn and from experience. But this is a core concept that I want you to understand, the idea of overfitting. Now, unlike decision trees and supervised learning, unsupervised learning is a method. For example, in the case of this fraudulent of transactions and using machine learning for fraud prevention, I mentioned that you could have some of your labels wrong, because there were probably fraudulent transactions within the ones that you saw were classified as not fraudulent, because the bank has just not identified these as fraudulent yet. And such data sets for which you have no meaningful label can nevertheless be put through what is called unsupervised learning algorithms to classify them, and then to cluster them, to find patterns within them, and then to identify some of which are anomalies. And an unsupervised learning algorithm, its main feature is that it does not require a label. For example, if you look at these pictures, it doesn't say these three are ducks, and it doesn't say this is a mouse and this is a rabbit. But if you give it to this algorithm, it will nevertheless classify the similar ones together again. It will nevertheless be able to do that based on its features. So one of the examples is it works like this. The objective of any clustering model is to determine patterns within data. If you give these data points where your features are x1 and x2, the clustered data, it will show you that there are a method of clustering will show you there are now 3 main clusters. But do you know there are only 3 main clusters? Let's see. More specifically, the purpose of a clustering algorithm is to divide data into distinct clusters made of data points that are very similar to each other but distinct from the points in other clusters. And the purpose of an algorithm like this is not that it will just give you these clusters. It is so that you can now visit each of these clusters and do more investigations on the data. So this is something to help the data analyzer. So I will now show you how k-means clustering works. It is the most common clustering algorithm. So think of, again, data with two features, one along x-axis and one along y-axis, and you have these many entries. So these features correspond to the columns of the data, and the number of entries correspond to the rows of the data. And the first step in k-means clustering is to just pick two random points as candidate, what you would call centroids. So here we have picked just these two random points, and you have to also choose the value of k you want. Here we have chosen k to be 2. The next step is to assign every data point to the nearest centroid. So you calculate the distance from each of the point to each of these the chosen centroids, and you, depending upon which centroid each data set has a smaller distance to, you assign a point, a data entry to a centroid point. The third step is to now find the barycenter of all the points that have been assigned to a centroid, and then move the centroid to that barycenter. So the barycenter is basically just the weighted average of the x and y coordinates of all the points. In this case, the data itself have only the features and there is no weight, so it is just the average of these points, and so you move the centroid there, and here again you move the centroid, and then you just repeat the process over and over again. So you again compute the distances of each of the points to each of the centroids, and then you compute. Then you reassign each data point to its corresponding centroid, and then you find the barycenter of each cluster again, and you repeat steps 2 and 3, which are essentially the same as steps 4 and 5, over and over again until you reach a description of clusters known as this. You do it many times, you'll notice that things are not changing at all after a point. Your clusters are stable, and that is how you arrive at your final number of clusters. At this point, you'll obviously have multiple questions. The first would be, what should be the number of k? The second is this trivial example I showed you works only because I took a very simple example where the number of where the distances along x and y axes are the same. If you were looking at real data sets, for example, the bank transactions, you will notice that the amounts will span values between, say, 0 and 10,000, whereas, for example, the value of money that was in the account before each transaction will be on much larger scales, and so you cannot use this data if the different features are on different scales, because the distances in this more than one dimensional space are not well defined. If the data itself each of the features have different scales. For this, one of the first things almost any data analysis does when feeding a bit of data to a clustering algorithm is that they will scale it. They will normalize each feature to have the same range. And there are simple codes that will do this, and there are multiple ways to do this. This will be something that we will go through in length on Monday. The third thing I want you to know is that k-means, because you start with a randomly selected centroid, is often not deterministic. So what that means is it will not always give you the same clusters as your final answer. It will stabilize towards the cluster, but it will not always be the same answer for the same data set, because you chose different starting points. So what people usually do is they'll use k-means. They will run the same algorithm multiple times and make sure they're getting the same clusters, etc. So to answer the question of what should be the value of K, for example, if data are distributed like this, for K equals 2, you will get these definitions of clusters. For K equals 4, you'll get these definitions of clusters. And for K equals 8, you'll get these definitions of clusters. And so then the question is, what should the value of K be? And that is, once again, like I said, it is to be determined based on your judgment, based on your computation cost, based on why exactly you are clustering this data, because you, in the case of the fraudulent transactions example I mentioned earlier, you are, in the case of unsupervised learning, you are literally looking for hidden fraudulent transactions. And so you want to investigate each class of transactions that you think are anomalous. So it is to be based on judgment and how many different classes you can examine independently. But one of the most useful concepts for deciding the number of Ks, for example, the value of K, is something called the inertia. So the inertia is within a cluster. It is just the sum of these distances between the final centroid and the final data point. So in this clustering, it is the sum of these distances between this final centroid and all the data points, and the sum of these distances in this case. And that is called the intra-cluster distance. Inertia is the sum of all intra-cluster distances. So if you take the sum of distances within this cluster, the sum of distances within this cluster, the sum of distances within this cluster, and the sum of distances within this cluster, that is the inertia. And then you can plot that as a function of the number of Ks, the number of clusters, which is the value of K you choose, and you'll usually get a curve like this. If the curve is steeply falling, it means that there is a significant benefit to adding, to increasing the number of clusters. But if the curve is falling very slowly, it means that as you add more clusters, this algorithm will become slower and slower. And especially in a case of the data set of something like 6 million data points, that is a concern. So after a point, you don't examine this. So for example, for the data considered here, you can go between 6 and 10 clusters, and that is yes.
Sir, so the K-mean clustering would mean that if we want to classify data and we don't know what should be the classification, type of classification, so simply data will be classified on its own.
Exactly. It's one of the first ways to to subdivide data into clusters, so that you can have an idea within the space of its features. So here everywhere I'm showing examples with two features. Here it's X1 and X2, just unlabeled. In this case, it's debt and income. And these examples correspond to simple cases within two features, but you already know that there are data points that belong together. So now you have instead of the large number of data points you have, more of the order of 20, you have just 8 individual cases you want to examine. And when we run it for our 6 million data points, I'll show you it'll nicely break into less than 5 or 6 different classes of transactions, and then you can examine each of them individually to see if some of them are suspicious. And so that is why it is. These are simple algorithms that if someone gives you a large amount of data and you don't know what to start with, this will help you get a picture of all the internal correlations, the internal patterns that exist within the data. And so it is an initial tool that is very good to get on with. So supervised learning and unsupervised learning, like I mentioned, supervised learning requires you to have some amount of labeled data. That is, from your past experience, you need to know that this is what fraudulent transactions look like, this is what honest transactions look like. but then they have their disadvantage that some of the things you thought were honest could actually have been fraudulent. It's what you're trying to find out. But nevertheless, if you have those classifications based on past extensive investigations, you can use them to predict. And if they are if the data are discrete, like I said, you can classify future transactions as either fraud or not fraud, so that to enable further action. But on the other hand, if the data are continuous, like I said, in the case of, for example, predicting something like a demand for a quantity, like medical oxygen, then you can use it. You use supervised learning to construct regressions to make predictions of what you'll need. The unsupervised learning, on the other hand, is helps you identify patterns and clusters within data if it is discrete data. If it is continuous data, it will help you do something called dimensionality reduction, which again is something I will save for future modules. Techniques such as you may have heard of them, such as principal component analysis, etc. They involve, let's say, once we go through the examples for the other three, this will look quite simple. Now, this brings us to the question: we want to use supervised learning after we trust the labels on a data, and we want to use unsupervised learning if we suspect some of the labels may not be correct, and we need to examine let's say to find fraudulent transactions that you may have no prior experience of catching. But what if like an entire data set is fraudulent? And this is a situation that people come across in various real life data sets. There is a rule that applies to various real life data sets that is in contravention to naive expectation. This is known as Benford's law. Benford's law states that the distribution of the first digit of many numbers in real life data sets is like this. That is, the probability of the first digit being 1 is something like 33%, whereas the probability of the first digit being 9 is less than 5%. This is in contradiction to expectation, because one would naively think that if these are numbers and they are uniformly distributed, then the first digit should also be uniformly distributed. So there are 9 numbers, and then you would think the probability should be, each of them should be 11%. But the probability distribution is actually given by this function. This is the logarithm to the base 10. And this law has been observed in various real life data sets. For example, if you take the 237 countries that exist in the world and plot the first digit of their populations, this is the distribution you'll see. It follows more of the Benford's law than it is not a uniform distribution. If you take, I don't know, I'm a physicist and many of you are engineering students, so you must be familiar with constants like Planck's constant or the ideal gas coefficient. You take a large collection of those and you take in any standard unit system and you take their first digit, it is also distributed according to Benford's law and not uniformly. What is the explanation for Benford's law? It is quite a complex phenomenon. This law has not been, there is no mathematical proof for it. There is no simple logical argument. But a simple argument is this: if there are real world distributions that span many orders of magnitude uniformly, then you can see that the fraction of red, which is the fraction that is in which the first digit would be 1, is given by is pretty uniform across many decades. And in such situations, Benford's law works quite well. So for example, electricity bills, street addresses, stock prices, house prices, Well, street addresses in some cases, not necessarily in all cases, but stock prices, house prices, death rates, lengths of rivers, etc. Benford law works very well. But if on the other hand, we know that your numbers are supposed to span only a narrow range, or if they are essentially sequentially assigned numbers, they will not follow Benford's law. The first digit will not follow Benford's law. For example, Benford's law does not apply to telephone numbers. It does not apply to ID numbers, etc., because these are sequentially, your Aadhaar card numbers, because these are sequential numbers that are assigned to entries. It will not apply to bank account numbers. It also does not apply to the heights of human beings, because the heights of human beings do not span orders of magnitude. Right? Everyone is like roughly between 130 and maybe max 220 centimeters. Now, no, I don't think anyone is actually 220, but I'm just being a very conservative. So it spans, just a factor of 2. It does not span many orders of magnitude. Neither will, for example, the IQ scores of human beings, because the IQ is actually the score itself is derived from a distribution that is meant to be normally distributed around 100. So 100 is the IQ is the average IQ of all human beings on Earth. So numbers like this, which are very narrowly distributed, will not follow Benford's law. But naturally occurring real-world numbers that span many orders of magnitude are expected to follow Benford's law. This is not something that has been very rigorously understood. There are some explanations based on, let's say, ideas that you will come across in thermodynamics, like entropy, etc. But you cannot really apply to any system and just classify the system and say, hey, Benford's law should definitely apply here. Benford's law should not apply here. Nevertheless, this method has been used extensively to detect fraudulent data sets. For example, polling numbers, the US media have quite often taken the election counts from various constituencies in, for example, countries like Iran, where people believe that the elections are not free and fair, and demonstrated that the digits in the number of votes counted for different candidates in different constituencies, the first digits are not Benford's law distributed, to suggest that there was evidence of ballot stuffing, etc. But the issue is, because there is no exact, there is no real proof as to what systems this should apply for and what it shouldn't apply for. It's really intuition. So in many countries, you cannot prove using Benford's law that something is fraudulent. So this should again just guide your judgment in applying further techniques that we already introduced to examine a data set. In the 70s and 80s, before all of these benefits transfers and social welfare schemes were made online and many real-time checking was introduced, it was quite often the case that people would just, if there was a lot of corruption, they would just make up accounting numbers or make up socioeconomic data. And in such cases also, you can apply Benford's law to understand to give you a guiding principle of if the data set has been made up or not. So these are some of the techniques that are used for fraud detection in data sets. In summary, we have introduced a basic idea of supervised and unsupervised learning today. What are the differences between supervised and unsupervised learning? The main thing being that for supervised learning, you already need a data set that you believe to be true, that you believe is accurately labeled. And since that is never the case 100%, as I said, as we taught in the previous lecture, there is always a false positivity rate and a false negativity rate. Every time you use a data set to train a supervised learning algorithm, like a decision tree, you need to also vet that data set by performing random tests on it, various tests on it, such as unsupervised learning tests, such as clustering. In Monday's session, what we will do is we will use a decision tree on the Kaggle data set that we already examined to, and you saw that it already had labeled data. So we will use that we will split the labeled data into training and testing sets. So we understand the ideas such as overtraining, overfitting, etc. that I already introduced. And then we will use a k-means classifier on a synthetic data set that emulates transactions of the National Payments Corporation of India to identify, because they don't, this data set does not have labels. So we will try and identify hitherto unknown but possibly fraudulent transactions. So this is what we plan to do for Monday. That's all for today. Do you have any questions?
Yeah, sir. So application of this clustering should be, I mean, this supervised and unsupervised learning should be in identifying the target audience. Like if I have a company and I want to launch a product, and I want to know what audience should be and what is the size of my audience. So that kind of application can be done with this.
Yeah.
If we have access to data somehow.
Sure. So, for example, if you have access to, let's say, all the purchases that somebody made on Amazon or everybody made on Amazon over the last year, then you can cluster it to find out what sort of people buy what sort of things. So it is possible that people who live in cities, they buy certain kinds of clothes, whereas people who buy in villages buy certain kinds of clothes. And to identify those kinds of patterns, you can use unsupervised learning, where in that example. If on the other hand, you have, for example, each of those transactions were initiated by people clicking on ads and an advertisement, from another website, and so you have that bit also logged. What advertisement did they click on, which led them to make this purchase? So then you have a label that allows you to identify what kind of advertisements lead to what kind of purchases, and so then you can use supervised learning to optimize how to advertise for a certain kind of product. Is that the kind of answer you are looking for? Or?
Yeah, that's what I was asking कि इसकी application कहाँ पर होती है? Yes sir. Okay, fine, thank you.
Yeah, so those are the generic applications of supervised versus unsupervised learning. But like I said, in Monday, I'll show you on Monday's tutorial session, I'll show you a very specific application wherein both are complementary, in the sense, like I said, in the 6 million transactions we are going to play with, some of them are not have been identified as not fraud, but they may be fraudulent, and the only way to look for that is to really cluster them and examine each one independently. And unless if you are the actual bank who can call up the customer and ask, hey, did you mean to make this transaction? You don't really know for sure, right? You can only investigate in a closer way. And investigating 6 million transactions is difficult, but investigating 8 types of transactions is much easier. And that's why you use unsupervised learning. Does anyone else have any other questions? So for things like the inertia, etc., there are standard formulae available. I did not write down those formulae because distances, etc., are intuitive, and when you code them, code it up, you will actually usually end up using the intuition. And in the case of using something called pandas or scikit-learn, you don't even need to actually code this up because all of this has already been implemented. So one of the
Sir,
advantages, yes.
sir, excuse me, sir. This is not related to this lecture today. Yesterday, I came across a graph of that was a normally distributed. So in that graph, on x-axis it was a frequency, and y-axis it was yeah, it was something else. X-axis it was something else, and y-axis it was frequency. So इन जब हम वो दूसरा वाला ग्राफ देखते हैं तो उसमें y एक्सिस पे क्या होता है सर, जो डिस्ट्रीब्यूशन होता है ना नॉर्मली डिस्ट्रीब्यूशन में x और
Um,
y एक्सिस में उसमें क्या
was
क्या
it a histogram?
नो 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 सर, इट वाज नॉट हिस्टोग्राम, इट वाज अ नॉर्मली डिस्ट्रीब्यूटेड कर्व। तो मतलब यही है कि जो नॉर्मली डिस्ट्रीब्यूटेड कर्व है उसमें हम वाई एक्सिस में क्या रखते हैं और एक्स एक्सिस में क्या होना चाहिए।
Okay. So
या
a normal distribution function is or the Gaussian distribution. It's called a probability distribution function, and what is plotted on the x-axis is something. Sorry, what is plotted on the y-axis is something called the probability density. So on the x-axis you have an interval, and on the y-axis you have a probability density. A probability density itself cannot give you a probability because it is an infinitesimal quantity, but you can integrate it between two points. So I mean, I can pull this up in a. I can wait my. I think I had shown you confidence intervals on the normal distribution in the previous lecture, but I can pull up a figure for it. Let me see. Um, for example, this is a normal distribution, right? Do you see this?
नो सर, या
Can you hear me?
यस सर, यस सर,
Yes. Hello.
यस सर, वी कैन हियर यू।
Can you see this?
यस सर,
Okay. So yeah, I don't know. Sorry, the Google Classrooms is it sometimes gets my computer in a curve like this. What is plotted along the y-axis? Sorry, the x-axis is something called the random variable. I don't. Sorry, my computer is quite slow. But yes, what is normally plotted along the x-axis, what is called the probability density function, and quite not a probability because, but the range is a probability. So from the center between one variance, one standard deviation below and one standard deviation above, it will contain about 68% of the probability. Does that answer your question?
यस सर, बट या सर, इसमें ना अलग अलग ग्राफ में कई बार अलग अलग होता है दिया हुआ। समटाइम इट इज इट शोज स्टैंडर्ड डेविएशन, Sometime it is something else. So that's why I was asking. I mean, y-axis is for a
No,
probability, and x-axis is for that particular variable. So
yes, but the y-axis is called a probability density. In any in a discrete distribution, like the case of coin tosses that Subodh introduced, or
yes, sir.
throwing a die like I introduced, you can think of what is on the y-axis as probabilities itself, because intervals on the x-axis have been already accounted for. But in a continuous distribution function, what is directly represented on the y-axis is not a probability; it is a probability density. To get a probability, you always need an interval on the x-axis. A point on the x-axis is not sufficient.
Okay,
Do
okay,
you,
sir.
do you understand what I mean?
Yes, sir. Yes, sir. It is a
Okay.
density. Yeah.
Yes. Yeah. That and I did not really get your comment that sometimes it is the random variable, sometimes it is something else. I did not
I
understand that.
mean,
You if you
sir,
show me
I
a real
mean,
example, I can tell you.
yes, sir. Like here in this, in x-axis, it was, सर अलग अलग ग्राफ में ना अलग अलग वो होता है दिया हुआ. कई जगह तो वहां पर ना स्टैंडर्ड डेविएशन से शो करते हैं, और कई जगह वो सिंपली वो ये लिख लेते हैं कि दिस साइड में इतने वेरिएबल पे इस पॉइंट पे इतनी इतना वो है, इतनी प्रोबेबिलिटी है. तो
Sure.
उसमें ना कई बार कंफ्यूजन हो जाती है कि एक्चुअल में होना क्या चाहिए एक्स एक्सिस पे और वाई एक्सिस पे. सो दैट
So
वाज द क्वेश्चन. या
the
तो
axis label should just be the random variable.
या
All the other things, the plus one sigma, the minus one sigma, etc., they're just things to visually show you ranges. If you
ओके
think of this as a proper plot, the axis label should just be the name of the random variable, like x.
ओके ओके
Don't be confused by that. It is, yeah, it's just if you're talking about heights of individuals, the x-axis is the height and the y-axis is the probability density.
ओके ओके फाइन. थैंक यू सर.
Does anyone have any other questions? Okay, so what I'll do is, tomorrow I will upload a Jupyter notebook for our entire Monday lecture, and the lecture will be in the notebook itself. And because I'll upload it in advance, you can play around with it if you want. Uh, that you can be prepared. If you want, you can do it while I am doing it live, or you can play with it before or afterwards. So I guess that's the best way to go about Monday's hands-on session, using these techniques that I taught you today on the data set I introduced earlier. Yeah, if you want to, so Subodh and I were thinking that for the second module, we will just, um, you know, create like uh, coding classes and just help you get started with uh, plotting and making and looking at large data sets, and to actually teach you coding. And for that, I guess it will be useful if all of you are on some group, whether it's WhatsApp or even a Google group or whatever. That's fine. So that's a
Yes,
good
sir.
idea. Please circulate it on the Google Classroom page, so that the students who are not attending live but who will be watching the videos later. So If that's all, then I'll see you on Monday.
Okay, sir.
Bye.